Okay, I can feel it just by looking at this, all you string sizing freaks out there. This is a string sizing question if I ever saw one. So let's read it. If you have PV with an open circuit voltage of 38 volts and an inverter with a maximum input voltage of 1000 volts in a location that will have a low design temperature 32 degrees below Celsius, assuming a typical temperature coefficient of VOC of minus 0.32% per degree C, what would be the maximum number of modules in series? So we're doing the cold temperature longest string sizing thing, and we could do this really, really quick. In fact, you know what? Before we even go through the answer, I'm just going to show you how quickly it could be done. So we've got our calculator there. It's 32 below. What's the difference between 32 below and 25 above? So we're just going to go 32 plus 25. And the delta T is 57. Multiply that times 0.0032 equals plus 1 equals times 38 volts equals cold temperature voltage. Divide that into 1000 volts, and it's divided into, so it's upside down. So I flip it over and I've got 22 in series max. There you go. That's how to do it quickly. So now let's look into it a little bit more in detail. 22 is the answer. So the step one, what we're looking at here is the delta T. And so we just did that. And these are the 4 things that we need. And remember, this is for cold temperature. It's a different calculation for hot temperature. So what we have is 32 below, way down here. 32, looks like these are 5-degree increments. And also we have Fahrenheit on the left. You can see that minus 40 Fahrenheit is the same as minus 40 Celsius. And that's the only time that those two different scales cross over. And so we're looking at minus 32 and then 25 above. And you just have to know that 25 above is standard test conditions, the way they test modules. So we're always basing it on 25 degrees. People are always asking me that. Like, how do they figure out where does that 25 come from? You have to memorize it. That's called standard test conditions. So 32 to 25. Another mistake that people commonly make is they think, oh, it's 32 above or something like that. Or sometimes the temperature isn't below 0. If it would be 5 above 0, then it would be delta T of 20 degrees because 25 minus 5 is 20 degrees. But here we're on different sides of 0. So it's going to be 32 plus 25. That's the way I do it. You can have your own way. But I think my way works pretty well. And these are the 4 things that we need for string sizing. The low temperature coefficient of VOC, the VOC, and the max inverter input voltage. So we wanted that delta T. We took 25 plus 32, and we can go on to step 2 here. And what we're looking at is the delta T, which is 57 degrees. And then we're going to multiply this by this coefficient, but we're going to turn that percentage into a decimal. So if we took 0.32 divided by 100, it's 0.0032. Another thing is always these coefficients are always just point something. Usually it's 0.3 something or 0.2 something or 0.4 something. In fact, it never is different than that for voltage. Just that's the way the crystal works, the silicon crystal. And so if you wanted to just have a shortcut that works for you, you just say you put 2 zeros there, 0.0032. That's what it's going to be. And just kind of goes, if you wanted to analogize that, to make an analogy, is that a word? Analogize? Sounds good to me. Then what you can do is you could say 50% divided by 100 is 0.5. And so if you're going to do math with 50%, you multiply by something by 0.5 to get 50% of it. So 0.32, you also would move the decimal 2 places to the left, divided by 0.5. And that's where we get this 0.0032. So 57 times 0.0032 gives us 0.1824. And I think in my head, when I get to this spot, I always want to make it make sense when I'm doing it. And so I think in my head that 0.18 is 18%. And does that make sense? And that does make sense. That when it gets 32 below 0, that I might get about 18% more voltage. And so I double check myself and I move on to step 3. And what I do here is I add 1 for a 100% increase over 18, because I want to figure out how much higher my voltage is getting, because it's getting colder than 25 degrees. So my voltage is going to go up. So I need a number greater than 1 to multiply by. So what I'm going to do for an 18% increase is I'm going to add 1 to 0.1824, and I get 1.1824. I can also call this my temperature correction factor. You also can see in the National Electrical Code, there's a table, 690.7a, that has all these temperature correction factors for different degrees, and it's just a different method than using the coefficients, but we usually use the coefficients because we are coefficient, or at least efficient. So now we've got this correction factor here, and we are going to multiply it by our STC VOC here, which is 38 volts. So we take 38 volts and we multiply that times that 1.1824, and we get our cold temperature corrected open circuit voltage, which is 44.9 volts. And I also think in my head, does this make sense that my voltage goes from 38 to 44.9? And yes, it does make sense. If you have an answer that doesn't make sense, like say that you got a number that was 80 or something crazy like that, you know that you got to go back and figure out why it doesn't make sense. All we have to do now is now we know what one module does, and we just want to make sure that we stay under 1,000 volts. 1,000 volts is the maximum voltage that you can have on a building, and 600 volts is the maximum that you can have on a 1 or 2 family dwelling, and 1,500 volts is the maximum voltage that you can have off the building on the ground. But you also have to double check to make sure that the inverter can handle that voltage. And so this is the maximum input voltage there. And we're going to just see how many times 44.9 goes into 1,000 for step 5. So we're going to divide this new VOC into the inverter maximum voltage. So I got 1,000 divided by 44.9 equals 22.3. And even if it was 22.9, I'm going to still make it 22 because I can't go over 1,000 volts. One of the things that happens is when you're doing the calculation, you end up with 44.9 in your calculator. So I have a little calculator shortcut where I would just go 44.9 divided by 1,000. So I don't have to remember anything or write something down. And so I go 44.9 divided by 1,000. And then as you saw me with my calculator, I hit the 1 over X key. That's the inverse key. And that would flip it. So if I had 4 in my calculator, I push inverse, it would go 1 over 4. It would go 0.25. And then I have 0.25, I hit the 1 over X, 1 over 0.25, hit the 1 over X, I get 4. And it would just keep going back and forth and back and forth. And so that's just a way to turn the numerator into a denominator and vice versa. So once again, we are rounding down because if we put 23 in series, even if it was close, we'd go over voltage. And so far, what we've done is answer the question, and that was for the cold temperature and the maximum number in series. Once you get that down, you might want to figure out what's the minimum number in series. And usually we like to keep the strings longer because higher voltage is more efficient. You need less current for the same amount of power. You need less connections. You need less fuses if you're using combiners. You have less strings if you're making more in series. But sometimes, for some reasons, people might want to know what would be the least amount of modules that they could put in series. And so let's figure out what we need for that. And so what we would need is the expected hot cell temperature. So before we took the low temperature and we didn't add to it for the heat of the sunlight and all that. And engineers sometimes will do that. And you can do stuff like that under engineering supervision. And that was for cold temperature under engineering supervision. Cold temperature is a safety thing. Hot temperature is just an efficiency thing. So it's not a rule. It's not in the National Electrical Code. Being inefficient, as long as it's safe, is not a code violation. And so if we had a hot ambient temperature of 40 degrees with sunlight hitting a solar cell, it's going to take it way over 40 degrees. And so what some people would do is just add 30 degrees to it. So 40 plus 30 is 70 degrees Celsius. Pretty hot. But hey, it's something that's colored dark that's in the sun that can get kind of hot. Then we find the delta T from over 25. And so let's say it was 70 degrees. Then the difference between 70 and 25, 70 minus 25, is 45 degrees. So kind of give you an idea. It's going in the other direction. You don't have that negative thing. You don't have to like add two numbers together. You're subtracting. Then we want to use the temperature coefficient of VMP. It's usually a higher number than the temperature coefficient for VOC. And usually you're not even given the temperature coefficient for VMP. So I would just use the temperature coefficient for power, which is usually the same as the temperature coefficient of VMP whenever I've seen both of them together. Then let's say that I had a 0.2, so a 20% decrease in voltage. Instead of adding to 1, I would subtract. So I go 1 minus 0.2, I get 0.8. Then I get my VMP, because we're talking about efficiency, and VOC isn't related to efficiency because it's turned off. It's a safety thing. It's your highest voltage. So VMP times 0.8, if it was a 20% loss, I would multiply those two together and then take that number, maybe it's 25 volts or 30 volts or something like that, and divide that into the inverter lower maximum power point tracking voltage. And then let's say that I got 5.5 in series. Then for this one, I have to round up to stay in the window. In fact, a lot of people won't even accept the right answer. If it was 5.5, they wouldn't just want to have at least 6. They would want to even do 7 because you might have voltage degradation over the years. You might have super hot PV, anything like that. So there you have it for your hot string. That's an efficiency thing. And we did it for the cold string. Once again, if I wanted to do it quick, it's good practice. You could be in the string sizing championships. So 32 below. So what I'm going to go is 25 plus 32 equals times 0.0032 equals plus 1 equals 1.1824. Check in my head, 18% increase. Sounds right. Multiply times the VOC at standard test conditions, which is 38 volts. Then I get 44.9 volts. Divide that into 1,000. I did it upside down. Instead of 1,000 divided by 44 point something, I did 44 point something divided by 1,000. So I'm going to flip it, and I get 22 in series. That is the answer.